All right, boys and girls, welcome back to the drive-through. We are in 10.6, Surfaces in Space. As always, the drive-through is sponsored by the deli. Hungry? Stop by the deli. Get yourself a chicken Philly cheesesteak with banana peppers, mushrooms, mayonnaise, and provolone. All right, we're going to conclude this chapter. Even though there is a 10.7 in our book, we will be coming back to that at the end of the year. So we're going to conclude this chapter for us by finishing some new surfaces, or finishing up the surfaces that we will be able to demonstrate with an equation. Okay? All of these surfaces will be able to be grouped into two different types of surfaces. So we have the cylinders and we have the oids. All right, so this is going to be an aggressive definition. Let C be a curve in a plane, and let L be a line not in a parallel plane, so that intersects the curve. The set of all lines parallel to L and intersecting C is called a cylinder. C is the generating curve, and the parallel lines are called the rulings. Okay, look, what this is saying is that a cylinder can travel in any direction. So it can travel up in the Z direction, it can travel out in the X direction, or it can travel across in the Y direction. But technically, it can also travel, in some random direction parallel to the vector 6, -2, 4. Now, I will tell you this. We're not going to be able to graph these if we don't just focus on the cylinders that are running parallel to one of the axes. So we will focus on cylinders, okay, that have rulings that run parallel to an axis. So, as you just kind of take a note, it's important to know that if the equation of a cylinder does not contain a Z, then the rulings, and you don't know what rulings are yet, so just relax and we'll get there. The rulings will run parallel to the Z-axis, okay? If the equation doesn't contain an X variable, then the rulings will run parallel to the X-axis, and the same is true for the Y. So let's just try these and see what the heck these rulings are, and you don't really even, eventually, it doesn't even matter if you know what a ruling is or not. That's my ruling on that. Notice, as a matter of semantics, if you were asked to graph x squared plus y squared equals 16, that would be a fine answer. Oh dear. Okay, that is the graph for x squared plus y squared equals 16. Now we're asked to sketch the surface represented by x squared plus y squared equals 16. Well, this thing is not a surface. Remember that when you graph a circle, you're graphing the set of points that are 4 units away. So you're only describing this set of points. That's not a surface, that's a curve. Okay? So a surface is 3-dimensional. Let's see now. A surface is 2-dimensional. A curve, I guess, is 1-dimensional? That's strange. I can't even really imagine that. You guys can think about that. But anyway, let me show you what a surface is, okay? Notice, no Z in that equation. That means the rulings will run parallel to Z. So, if I, again, the best we can do is just sketch this. So you don't have to be a perfect artist. Believe it or not, I'm not. And that's a total joke. I'm awful at art. Art. Okay, so it's important that we label our planes, or our axes, okay? The base is going to be a circle in the XY plane. I understand that. So I need to add some. So that point, this point, and that point are all going to be on the Generating curve. Okay, and that's the generating curve. I don't like that at all, so we're going to try that again. It really should just look like a flat over. Okay, that's not great, but it's not terrible. We'll go with it, okay? Let me just make that look a little better. All right, so there is a cross-section of our curve. Now, the rulings can be demonstrated on this if we understand that z has no limitations, okay? So z has no limitations. So there is a sketch of this cylinder. Now, it also goes down forever in the negative z direction. Okay? So notice that when we're graphing this equation, the lines that are not in the plane look like this. Those are called the rulings. Okay? Those are the rulings. And they are parallel to the z-axis, and this equation does not contain a z. Let's try another one. Sketch the surface represented by z equals the sine of x. Okay, sketch. Z equals the sine of x. Well, sine of 0 is 0. We're coming positive. So the sine of pi over 2 is 1. It's going to be somewhere up here. And we got something like that. Okay? And it will also be going... Okay, now, y has no restrictions. So notice y is not involved with this shape. Sorry, with this equation, which means anything could be y. Oh dear. Here we go here. Let's see. This is tough. Parallel to y. Let me do this in a different color. This should be parallel to y. That should be about the same length. Okay, and this should be parallel to y. And then if I just... Who is shaking my board? Okay, we have... Maybe you can start seeing the shape develop. So, let's see. You can certainly see that here. We've got some traces. And then there's one, and there's one, and there's one, and there's one. Okay, now it starts to get ugly over here. Let me just erase this. Okay, I'm just going to leave it like that. This is the best I can do to graph z equals the sine of x. You can imagine it like a roller coaster. Now maybe in the future it might be advantageous to just rotate our axes. So let's see, right hand rule. I'd like to just write the curve like this. Let's see, like a typical sine graph. Okay, and then let's take this and write it like that, and this would be a trace parallel. I'm trying to make, let's see, this doesn't involve y, so that would be my y-axis. So let's see. You need a trace there, a trace here, a trace there. Hold on, let me show you why these don't look great. They need to be parallel to that, the traces do. So this would look perfect if I did it like this, like this, like this, like this. If I erase this one here, and make that like this. Okay, that's the best I can give you. Now this is going to continue. And then this is, and I don't know. That's what I got. Okay? All right. Now, the oids. All of the oids are going to be written into the equation. That is awesome. It's ax squared plus by squared plus cz squared plus dxy plus xz plus fyz plus gx plus hy plus iz plus j equals 0. Holy cortex surface, Batman. Alright, so don't freak out about this, okay? Here's what you're going to have. The oids, there's 6 of them. Okay, there are 6 oids. Everybody say hi to the drive-thru. Okay, here's your oids. So look, in this ellipsoid, plus, and 1. Okay, notice A, B, and C are different, so that gives us ellipses in each trace. So when it says the plane, okay, you can just see that this little thing here is the xz trace. It's like we sliced it with the xz plane, okay? If A, B, and C are all the same constant, then what does this ellipsoid become? A sphere, okay? A sphere. Here's the hyperboloid, thank you. The hyperboloid of one sheet. I couldn't get hyperbolic geometry out of my head. The hyperboloid of one sheet is plus, minus, and 1. Now notice, if this is an x and this is a z and it's minus a y squared equals 1, then this little nuclear reactor is going to be rotated around the y-axis. Okay? So you have to understand how to read this thing. This is a hyperboloid of 2 sheets. Notice it's a positive, a negative, and a 1. Okay? This is an elliptic cone. It's an elliptic cone because A, B, and C are not necessarily the same. So while this thing right here looks like a circular cone, it doesn't have to be. Those are ellipses. And again, if you change this x squared to a z squared, and if you had z squared over a squared plus y squared over b squared minus x squared over c squared equals, notice this is a 0 now, well then this thing would be rotated about the x-axis. It would be facing a different direction. Here's your elliptic paraboloid, and here is your hyperbolic paraboloid, better known as a saddle curve. And then here's the coolest thing about a hyperbolic paraboloid. That point right there is both a relative minimum and a relative maximum at the same time. Mind blown. Boom!